Okay, so welcome back. We'll finish up here with our last video in probability. And what I want you to do is think about an experiment here once again. So we're going to go back to the experiment of drawing two cards from a deck, but we're going to do it what we call with replacement. So that means the first card will be drawn from the deck and then put back in, shuffled up, and then the second card will be drawn. So in this particular experiment, what's the probability that the second card that's drawn is hearts? If you know nothing about the first card, just in general, what's the probability that the second card that gets pulled is hearts? The answer is, well, no matter what that first card was, it got put back in the deck got shuffled, which means there was 52 cards for the second person, 13 of which were hearts, and so the likelihood of getting hearts on the second card is just 1 out of 4. It doesn't matter what the first card was. And this is in fact a conditional probability, isn't it? If I let A be the event of drawing hearts first, and B being the event of drawing hearts second, then what we just said is the probability that the second card is hearts, assuming that the first card is hearts, is 1 out of 4. And I can replace A with first card hearts, first card clubs, first card spades. It doesn't matter. The point is that when I set my events like this, A and B, A relates to the first pull, B relates to the second pull, then the conditional probability of B given A is identical to the probability of B itself. Okay, and so if this happens, then we give these two events a special name. We call them independent. And what that means is that the occurrence of one event did not impact the likelihood that the second event happened. In that example, we just saw how the probability of B given A was the same as the probability of B. This means when I add an assumption that B happens, or A happens, it doesn't change the likelihood of the other happening. And anytime I have two events relating to sort of separate pulls from a deck of cards, where those cards are put back in and reshuffled, whatever happens on one pull doesn't affect on the other. That means these will be independent events. When events do impact the likelihood of the other one occurring, like we would see when cards are pulled from the deck without replacement, we already saw how pulling hearts on the second card changes when I assume that I pulled a heart on the first card, then such events are called dependent. Independent and dependent events. And so a nice thing happens when we do actually have independent events, and it refers to how we can calculate probabilities, but we can actually follow a nice little multiplicative formula for finding probabilities with the assumption that these events are independent. So usually this comes to light when we have things like separate trials of a probability experiment. So separate draws of a shuffled deck, or an experiment that involves first rolling a dice and then second pulling a card from a deck. When the events truly are independent, then it makes it a little bit easier to find some kinds of compound probabilities. So here's another example. Suppose I draw two cards from a deck with replacement. A is the event that I draw hearts on the first card. B is the event that I draw hearts on the second card. My question is, what's the probability that both A and B happen? What's the probability of A and B? So this is, what's the likelihood that both cards come up as hearts when I pull cards from a deck with replacement? And we actually found this already, I think, didn't we? Maybe I just did it in class. But the probability A is 1 out of 4. The probability of B is 1 out of 4. And a nice easy way to find A and B, well, I do remember doing this in class. How many total ways are there for me to draw two suits? Well, I have hearts, hearts, forgive my crude drawing, of course, hearts, clubs, hearts, diamonds, etc. There's 16 total ways. This is just a fundamental counting principle that I can draw both cards from the deck when I only worry about their suit. And so if there's 4 different ways for me to draw the first card, 4 ways to draw the second card, there's 16 ways for me to draw two suits. And since all of these outcomes are equally likely, the probability of both A and B happening, that means the probability of me getting hearts and hearts is just 1 out of 16. And 1 out of 16 is equal to 1 over 4 times 1 over 4. And so when events are independent, because getting hearts on the first and getting hearts on the second are totally independent when the card is replaced, I can multiply 1 out of 4 by 1 out of 4 and find the probability. So this little formula will hold for any independent events. It's called the multiplicative rule. If two events are in fact independent, then the probability of both A and B happening is equal to the probability of A times the probability of B. So, does it work if the events are dependent and not independent? Well, quite simply, the answer is no, it doesn't quite work. And to think about it, let's just think about this example. We know that our classic example, or example so far of independent events, is the ones of drawing two cards from a deck with replacement. And if I draw cards without replacement, we already said that these are what we call dependent events. The likelihood of me pulling hearts on the second card changed when I assumed that I pulled hearts on the first card. And so the question is, would this formula work for if I replaced, A and B from the experiment of with replacement to without replacement? So the question is, well, I know that the probability of getting hearts on the first card is 1 out of 4. The probability of getting hearts on the second card is 1 out of 4, with no added assumptions. But what's the probability of me getting hearts on both cards if that card is not put back in the deck? Do you think if I'm not putting the card back in the deck, then it's less likely for me to pull 2 hearts, as opposed to if I was putting the card back in the deck? What do you think? Think about that for a second. And so the answer, quite simply is no, this rule doesn't work if these events are dependent. And the reasoning, it's a nice thought experiment to try to understand why this doesn't work. And so to get an example of dependent events, let's think back to the cards. So my experiment here is I'm drawing 2 cards from a deck without replacement. So I'm showing one person my deck of cards, they're pulling a card, and then the second person is pulling a card. So if A is the event of getting hearts first, B is the event of getting hearts second, then the question that I'd like to ask is, what do you think the probability of A and B happening is? Forget about this stuff here for a second. Just think, what's the probability of A and B? What's the likelihood that 2 hearts are drawn? Now, when that card is put back into the deck, that's 1 out of 16. That's what we just saw. We just saw that in the event, or in the experiment, where the card is put back in and reshuffled, I have a quarter chance on the first pull and a quarter chance on the second pull, which gives me a 1 in 16 chance. Do you think it's less likely to get 2 hearts when that card is not being put back into the deck? Do you think it will be less common for the same suit to be drawn twice when the card is not put back in the deck? Think about it for 5 seconds. And the answer is yes. If I'm not putting the card back in, then whatever card the person pulls first, there's 1 less of that suit in the deck. So they have a slightly smaller chance of pulling 2 cards from the same suit without putting the card back in. If I wanted to find the probability of A and B, that's the probability in this example of getting 2 hearts, getting a heart on each pull, then, well, what's the likelihood? First card, my chances of getting hearts are 1 out of 4. And on the second card, my chance of getting hearts is not 1 out of 4. So I can't multiply by 1 out of 4. It's 12 out of 51. So the likelihood of me getting hearts both times is not 1 out of 4 times 1 out of 4. It's 1 out of 4 times 12 over 51, which gives me, in this case, 12 out of 204. The pen isn't working here very well, which is equal to approximately 0.059, which is about 6% of the time, about 5.9% of the time. And the important point that we're trying to make here is that this is a different number. 0.059 is not the same as 1 out of 16. It's relatively close. 1 out of 16 is about, what's that, 0.0625. So they're fairly close probabilities, but they're not the same, right? I have a better chance of pulling the same suit twice when that card is put back in the deck as opposed to if it's not. And that's the point. So in order to find the probability of A and B, if my events happen to be independent, then I can multiply the probability of A by the probability of B. But if they're not independent, if they're dependent, then I can still find this probability by multiplying the probability of A by the probability of B given A. And what happens is that if they are in fact independent, then the second probability is just probability of B. So this is the multiplication rule in its final form. No matter what my events are, A and B, I can find the likelihood of both events happening by multiplying the probability of A by the probability of B given A. Okay, so let's just do a quick example about how we can use this multiplication rule to help us find a probability. And so we'll look at this question here about breast cancer. So true facts and true stories. Research has shown that there's a particular gene, they call it here the BRCA gene, where 1 in 400 women actually carry this gene. Okay, and out of those who do carry the gene, 60% of those women will develop breast cancer at some point in their lives. It's a very serious situation. And the question that I want to know is, what is the likelihood that a randomly selected woman from the entire population, based on these figures, will carry the gene and develop breast cancer? Okay, so we're looking for, out of all the women in the world, what's the likelihood that she has this gene and that she will develop breast cancer at some point in her life? So how would I find this? What I want to do is I want to set up some probabilities, some events, excuse me. So what do you think I should set A and B to be? Let A be the event that what? And let B be the event that what? And then how do I classify this probability that I'm looking for at the end in terms of A and B? Try to set that up first before you watch how I do it here. So take 5 seconds and I want you to say, let A be the event that something, B be the event that something. And what do we want? We want to find what? The probability of A and B, A or B, A given B. Think about it for a second. Try to set it up before you see how I do it. Okay, so what did you do? What did you do? Well, there's only 2 real things that I can consider here, right? I can consider when a woman has breast cancer or when a woman carries the gene. So let's let A be the event that the woman is carrying this particular gene, and B be the event that she will develop breast cancer at some time in her life. Then what's the probability that I'm looking for? I'm looking for the probability that a randomly selected woman will carry the gene and develop breast cancer. So this whole question just revolves around me finding the probability of A and B. And if I use my multiplicative rule, then I know that I can find the probability of A and B by finding the probability of A and multiplying by the probability of B given A. So what do these 2 probabilities correspond to in this particular case? What's the probability of A? A is the event that a woman will carry the gene. If I randomly select a woman from the population, what's the probability she carries this gene? Well, it's given to me in the question. It's 1 in 400. And the second thing I need to know is what's the probability of B given A? Meaning, if I randomly select a woman from the population, but I assume that she carries the gene, so I'm only concerned with those women who have this gene, then what's the probability that she will develop breast cancer? Well, that's given to me right here too. That's what this 60% is. This is the likelihood that a woman who has the gene will develop breast cancer. And that is 60% or 0.6. So according to my multiplicative rule, the probability of A and B is found just by multiplying these 2 numbers together. I find the probability of A, the probability of B given A. This is my, too many zeros there. This is my probability of B given A, this is my probability of A. And when I multiply it together, I find it's 0.0015. So I conclude by saying that's about what? That's about 1/10 or 2/10%. The probability that a randomly selected woman will both have this gene and actually develop breast cancer is about 0.1%.